maybe I'll start with a quick little summary of what we've done, where we're at. Let's see, so things that we've covered so far. So supervised, unsupervised learning, right? And so this was stuff we talked about last time. So we covered clustering, and there's a couple of different techniques that we talked about here. K-means, we talked about DB scan, and what was our other one? I'm totally blanking here.
Hierarchy?
Yes, hierarchical, thank you. Hierarchical. Okay, so that's all stuff on the unsupervised side of things. There's also dimension reduction, which we don't cover, but I'll kind of list that as, you know, potential other area folks are interested in. You can look into that, or if we have time, we might be able to cover some of that. Supervised learning. We have kind of, I'm going to maybe put in a little bit of extra notation here. So we have kind of more stuff on the predictive side of things, and then things that are kind of more on the causal side of things. And I would say, so for logistic, this is kind of a pretty basic framework that falls into kind of both categories. This is a lot more foundational stuff, and so you would learn about like a logistic regression in, you know, an econometrics class, but this is something that you would also cover in like a machine learning class. What else did we talk about here? Something like K and N, and this would definitely fall more kind of on the side of thinking about predictive models. Okay. For continuous, we've talked about linear models. Again, this is kind of the analog to the logistic. You're going to learn, right, the basics of this in both. But we have covered techniques that are kind of more on the causal side. So things like our fixed effects, differences, and IV regression. Right, so these guys are definitely going to be more sort of on the causal side of things. And then we talked about venturing more into kind of non-parametric modeling. So what we have here, stepwise, polynomial, splines, and kernels. And so as you get to this level of stuff, you're more kind of solidly in the predictive space. And then I would say the GAN, the general additive model, might be something that's a little bit actually in between. It's trying to get some of the benefits of. And so today, we're going to cover some more predictive side of things in the discrete territory. And so we're going to talk about some pretty commonly used tools in the machine learning area that are leveraged to a little bit more on the predictive side of things. So we're going to be working our way up to what's known as a support vector machine. Okay. Yeah. So I think we kind of jump around in topic a little bit. So I wanted to spend the beginning of this class just to kind of get the lay of the land again, and kind of see where we're going with all of this. So does anyone have any questions about any of this before we start? Yeah.
A support vector what?
Support vector machine. I'll write it out in a second.
Okay.
Yeah.
And stepwise and polynomial are predictive.
They're kind of like, yeah, I mean, if I had to put them into a bucket, I would say they're more kind of in the direction of predictive, although, with stepwise and polynomial, technically, the betas could be interpreted in ways that you could make inferences about them, right? But they're, I would say, developed more to be, in the direction of predictive. Yeah. Yes?
What makes one side supervised and another unsupervised?
Yes, right? Okay, so this means, supervised means that you have explanatory variables. In other words, you have a y, and this is no explanatory variables. So really, these guys on this side, these are very, very much like different sets of models for very different sets of things, right? When we talk about supervised models, that means you are always kind of relating your analysis to a particular outcome, and you have the ability to verify and validate how your model performs relative to the outcomes that you're measuring against, right? So with Y's, we talk about validation and like cross-validation, out-of-sample validation, all of that kind of stuff. And then, maybe that's a little bit less emphasized on the causal stuff, but with the causal stuff, you are thinking about the relationships between treatments and outcomes, right? So everything kind of relies on having outcome variables that you are, measuring in some way, whether you're predictive or causal. On the unsupervised side, we don't have any of that. There's no right answer or anything. You're more concerned about how things are related to one another based off of distance or density or that sort of thing. Okay. Any other questions? Okay. So we are going to talk about support vector machines today. That's like the build up of today's lecture. And it's kind of going to happen in a similar way as we talked about going from stepwise to polynomial to splines, right? And so we're not going to start with the support vector machine. We're going to start actually with something a little bit simpler. But before we get to any of that, let me give a quick definition, which is relevant for the stuff that we're doing today. A hyperplane. This is a flat, affine subspace of dimension p minus 1 in p dimensional space. Okay, what does that mean? So let's say we are operating in 2D space, and we have an x1 and an x2, and you have a bunch of points like so, and you have a bunch of points like so. So this is kind of like that movie example that we did when we were talking about logistic regressions and k-nearest neighbors, right? Remember, there are points have discrete values associated with them. In that example, it was about the movie rating, right? It was like G, PG, PG-13, and R. And so that was classified by color. And then in that example, it was like the audience rating and the runtime, right? So as a variable, as you vary over each of those variables, you might have like a categorical change. And then in the logistic regression, we could see there were like these dividing lines for how that model would predict an outcome would be depending on where you were, right, in your x1 and x2. So a hyperplane is basically that dividing line. Okay, so this is a hyperplane. So if you look at the definition, right, it's of dimension p minus 1 in p-dimensional space. So we are in 2D space. A hyperplane is a line in 2D space, which is a 1D object, right? And you can imagine as you go up in dimension, it's the same thing, right? So if I'm in 3D and you have a cloud of points, then the hyperplane would be a flat 2D plane cutting through your 3D plane. Okay? Pretty straightforward, hopefully. So this could be described something like this: beta 1, x1, beta 2, x2 equals 0 in 2 dimensions. And then generally in p dimensions, this could be something like beta 0 plus beta 1 x1 plus beta 2 x2 plus dot 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 plus beta p xp equals 0. Okay? So these are the things that would describe that line. Okay, so that's kind of the foundation of what we're talking about today. So starting off, we will talk about our first building block is something called a maximal margin classifier, also known as the optimal separating hyperplane. So this is, whoa, crashing. Okay, we're back. Okay, so there's a couple problems that we need to think about with something like what I just drew. I want to draw a hyperplane that separates my categories of points, okay? And the problem is, what is the problem with doing that?
¿Necesito organizarlo?
Yes, exactly. In the same way that, remember like early on in the class, I had you guys draw different lines to go through points, right? In the linear regression, there's almost like an analog here, right? I could draw this one, this one, this one, this one, right? In fact, there are an infinite number of separating hyperplanes. Okay, an infinite number of hyperplanes. So okay, let me do this. Here's 1, 2, 3, 4, 5. Okay, put up your fingers and vote for which one you think is the best hyperplane. Okay, 2, 2, 2, 2, 2, 3. A lot of people voting for 2, 3. Okay. So who voted? You voted for 2.
Me?
Did you vote for 2?
I did.
Yes. Why did you vote for 2?
I heard someone say 2 out loud, so it's like peer pressure.
Okay. All right. Who did you hear say 2? Let's
Sarah?
why 2?
Seems like it's the same distance for each group.
Okay, great. So you are coming up with a quantitative reason, right? So a quantitative logic behind choosing that line, which is great because this is the same thing that we're going to do for our linear regression, right? We kind of look at it and we have an intuition about why a line fits through the points. We talked about how that intuition might be translated into like a quantitative measurement, and we can do the same thing here. So you are saying that it's kind of, it has to do with kind of the distance that the hyperplane has with the points in the plot, right? And that's actually exactly how a maximal margin classifier works. It is, so this is known as a separating hyperplane. So that just means that the hyperplane separates the categories of points. That is farthest from training observations. Okay, so how does that work? So let me draw this again. Okay, I'm pretty bad at drawing these, so give me a quick moment here. Okay. Something like this. Okay. So I have a hyperplane, and the way that you actually measure the distance is via something called a support vector. Okay, that's where the support vector comes from. A support vector is, imagine that your points are being held up by pillars that run perpendicular to your hyperplane. So that means something like this. Right? It has to be perpendicular. Okay, so these are my support vectors. Okay, and the idea with the maximal margin classifier is that I want to look at the shortest support vector, be it like the distance from the point to my hyperplane, and I want to maximize that distance. Okay, I want to make this support vector as far away as possible. Okay, so question, if this was the point, if this was the only support vector, where would I want to put the hyperplane?
Really far away from it.
Yeah, yes.
High.
Infinitely far away, okay? But if I have 2 points, then I care about maximizing the distance to the smallest one. I can no longer throw this super far away because as I move this hyperplane out in this direction, it gets closer to this, right? And if I move this hyperplane out this direction, it gets closer to this. And then I can angle my line in certain ways, and at some point it'll get too close to other points, right? So, actually your support or your hyperplane actually only cares about, you know, the shortest one, and the rest of the points have no effect on the hyperplane unless the hyperplane moves in such a way that this no longer becomes the smallest one, okay? So you can kind of think of like the points as like sandwiching your hyperplane in such a way that any way that the hyperplane moves, it will actually get closer to one of your points. Yes?
If it were only that one point, you probably wouldn't use this, like, if it was only one point, it would be like almost 360 away, like, but if it's p dimensions, it could go in any direction away from the point. Like, it starts at the axis, is it constrained to the Cartesian plane?
Yeah, it's gotta be in this graph somewhere.
Close to x2.
I'm not sure what you're saying. So like,
Could you go outside of the 2 dimensions? Like, are we speaking of p dimensions?
yeah. It has to be on the plot. Okay, it can't like disappear from the plot. The hyperplane has to be in there. It has to be defined by x1 and x2. Yeah.
Does this only work when we're doing 2 clusters? 2 groups?
Yes, you're ahead of the curve today. So you can do this for more than 2 categories, but you would need more than one line, one hyperplane. Okay. Actually, we're not going to talk about that today, but you can, yes, you can have more separating hyperplanes. It is possible to do that, yes. Okay. So the math to do this, you just maximize m for beta 0, beta 1, beta p comma m, such that p j equals 1, beta j squared equals 1, yi looks something like this. Greater than or equal to m for all I 1 to m. Okay. So if you plug this into an optimizer, something that looks like this, right, and your yi has different categories, it says 0 or 1, we're going to do just the simple case for now. You can solve for your betas in this optimization and it'll spit back to you all of your beta values, which will help you define what the hyperplane looks like, okay? So you have betas that essentially tell you what this hyperplane is. So this is very similar to, again, recall in the logistic regression, when we have categories of points and then you have some line that will say, basically, if I'm in this territory, I'm blue, and then if I'm in this territory, I'm red, right? So from a predictive model standpoint, that's what this hyperplane will tell you once you have the betas. Okay? Any questions about that? Great. Does anyone see any problems with the maximal margin classifier?
It's like a regression.
No?
How is it different from a regression?
No, this is a type of regression, I would say. I mean, the machine learning people will be like, no, this is a classifier, but classifiers are regressions. It is different from regression, right? You're not doing like a best fit line or anything like that, right? This is like a separating line. And we're separating two groups.
And what if there were 3 groups?
Yeah, so that was the question from earlier. We're not gonna, well, maybe I can show some stuff if we have some time. But yeah, you would have multiple hyperplanes, separating hyperplanes for multiple outcomes.
If your groups overlap,
Yeah.
will you maximize the negative number?
Well,
Not really.
no. So according to the rules, right, it has to be a separating hyperplane. So it's a straight line that separates all the points, right? So what if I have a red line here? Okay. Who wants to draw me a hyperplane that separates these two groups? Can anyone do it? Yeah. So that is the most common downfall of the maximal margin classifier. So pitfalls. So one is the non-separable case. And this is like also very common, right? So if I have x1, x2, and I do my same old stuff like before, but then if I have, bam, one point like that, you can't do a maximal margin classifier anymore. Just doesn't work. There is no hyperplane that exists that separates everything into two groups. So yeah, seems like a pretty strong pitfall, which it is. And you can imagine we're going to talk about an extension of this that will allow us to deal with this issue in a moment. There's one other thing that I want to bring up, and this one is slightly less obvious, okay? And that is sensitivity to individual observations. Okay, I will attempt to do this again. So, x1, x2. So if we have some points, these guys actually don't matter. Let's do something like this. And then these guys don't matter. Okay, so if I draw a line here, maybe, okay, that's better. Actually, I don't need to do this one. Okay, so this would be my separating hyperplane, and I have support vectors for these guys, and basically the idea is that any way that I move my hyperplane, it's gonna get closer to one of the points, right? And so this is the optimal hyperplane for the maximal margin classifier. But what happens if I were to like add a point over here? Suddenly my hyperplane would have to change, right, to separate them, and my new hyperplane might look something like this. Okay, and so your hyperplane gets shifted. Okay, makes sense to everyone? So the whole idea is maximum margin classifier can like, the separating hyperplane can swing wildly as I add more and more points to it. So it's very sensitive to individual observations. Okay. Any questions about that? So let's move over and talk about the support vector classifier. So one was our maximal margin classifier, and now we're going to build up from that, and we'll talk about a support vector classifier. So this offers some benefits over the MMC. So this would be the SVC. So general robustness to individual observations. And better classification. Of most training observations. Okay. So an SVC has the same optimization as the MMC, but one additional set of constraints. And that is epsilon I is greater than or equal to 0, comma, the sum of I equals 1, and epsilon I is less than or equal to C. And this C is known as our tuning parameter. So now our equation looks something like this. And this is known as our slack variable. So I'm not gonna like really go into the way the math works, but essentially the only thing you need to take away from this is that you have something, this slack variable, epsilon I, which tells us how many points can violate the margin. And C tells us the bounds, it bounds the number of epsilon i's. Basically the idea is you've got this m times your slack variable, right? If you have 0, which means that no points can violate the margin, then we're back to our MMC, okay? And so yi essentially has to add up to our m classifier. So you have to have the same number of points getting defined by y as what your classifier does. But then if I add a slack variable, then if epsilon I is larger than 0, then you can see the m term actually decreases in size. It's multiplied by 1 minus something, right? And that essentially allows this classifier to not perfectly separate all of the points. And then c is a generic like tuning parameter that basically tells you how many, it's a bounding limit on what your epsilon I would be. So this is like your budget for violations. And at c equals 0, same as NMC. Right? If c equals to 0, if you set c equals to 0, your SVC is the same thing as the MMC. Okay. So in this case, I'm now allowed to draw a separating hyperplane that may violate some number of grouping classifications across the line, right? And so if you allow for one violation, right, there can be like one blue point inside of the red points. If you allow for 2, you can have up to 2, and so on, right? So how do we pick the right C? How do we know what the right number of violations to allow would be?
Cross-validation.
Cross-validation, yay. That's right. So I can leave out a bunch of points. I can put in the hyperplane. I can decide how many penalty terms I'm going to allow, draw that line, and then predict based off some test points how well I've done, right? How many I'm guessing correctly, how many I'm guessing incorrectly, and you want to choose your hyperplane to maximize the number of like correct predictions that you're going to get. Okay? So that's exactly right. Cross-validation is going to, again, save our skins here and let us figure out what to set the tuning parameter to. Okay. So let's keep thinking about drawbacks here. I'm going to draw, or pitfalls of these models. Okay. Let me draw some points here. Okay, we'll do something like this. And then okay. So can I draw a hyperplane here using a support vector classifier? What do you guys think? I see you nodding your head. Yeah. Sure, why not, right? Because now I'm allowed to violate the groupings. So I could draw, let's see, maybe something like this. Okay. And then I would might be violating a couple points here, right? So I would just need to make sure my C is large enough. And maybe this is the best one, maybe it's not the best one, maybe I could get at a one where C is actually lower if I move the line down a little bit. Right, but this works. This is something that the SVC could actually do. So drawbacks. What do you guys think? Yeah.
There's clearly a non-linear divider which would work better in this.
Yeah. Okay. So you are talking about this, right? If I drew, yeah, something like this. So yes, this is fundamentally an issue with the support vector classifier is SVCs must be a linear separator. Yeah, that's exactly right. That is one of your inherent drawbacks of your SVC, right? Compared to the MMC, we've kind of dealt with some of the issues, right? We dealt with the issue that you could have mixing of points across the groups, and we've even kind of dealt with the fact that that the hyperplane can be perturbed a lot with a single point, right? You could, in theory, just let it violate and still keep your hyperplane fairly stable. So it is robust to some of those drawbacks. Okay, so then how do we deal with this drawback? And we do that via we're going to do that using our third and final one, the support vector machine. So this is SVM. So this one is the commonly used one. So SVM is a super common machine learning classifying tool that's used, right, to create separating hyperplanes that don't have to be linear. So how do we go from linear to nonlinear? So we've covered this, right? We've talked about, as we go into semi-parametric and non-parametric territory, what's one thing we could do? So we could allow for polynomial expansion. Or interaction of x's. But this explodes in size very quickly. So you can kind of go the direction of this like polynomial thing, or thinking about these hyperplanes kind of in a similar way as the splines, where we allow for bending via knots and through a simplified polynomial function. But actually, turns out it's a little bit easier for support vector machines to go the other route for non-linearization, non-parametric. So this is, so instead we can modify and generalize, which is very important, computation of the SVC. So if you assume, so SVC uses a linear kernel. So it's looking just at that support vector in like a linear perpendicular to the hyperplane thing. But in a SVM, you can employ more complex kernels. So the common ones are polynomial kernels and radial kernels. So the whole idea with the hyperplane is that, right, you create these pillars that define what that hyperplane looks like. With a support vector machine, it's similar, except now you are considering like swaths of points together as they relate to your hyperplane. Okay, so if you guys remember, with kernels, we think about the bandwidth, which is like how far away I'm looking. So in the same way, you're kind of making it so that your hyperplane is defined by how far away you're looking to like the closest points, and then it's going to try and do this hyperplane thing locally. So principally, this is just building off of things that we've learned, right, with the kernels. Okay, so let's take a look at implementing this in R. We're going to use a couple libraries here, and I believe I put all the resources on Canvas already that you need for this. Data table, we're going to use ISLR and ggplot. Okay. So we're going to look at support vector classifier example. And this time, so that we can all kind of see the same thing, I'm going to use setSeed, which is a way that allows me that when I do a random draw, that everyone will do the same random draw. So we're going to do 40 random draws into a 20 by 2 matrix. And that's our x, oops, not t. Y is -1, c, 10, 10. Okay, so, oh, I didn't run my x. My x looks something like this. And my y, oh, can I not do that? My y looks like this. Okay, so I'm ordering things in a certain way, and let's plot this and see what this looks like. Okay, so we've got, I don't need to blow this up, you guys get the idea. So 2 groups of points, red and blue, and we want to use, so would an MMC work for this? What do you guys think? Yes, no?
Yes.
you sure?
Marginal, maximum margin classifier.
Means that I would have to draw a line to separate these two groups.
Without the exception part,
Yeah,
so no.
so no, that's right. So MMC would not work, so we would have to run a support vector classifier which does allow for violations. Yeah,
Can you just really quickly explain what line 10 is doing?
yes, okay, so let's see. So I'm gonna make an assignment to my x's. I'm only going to make an assignment to x's where y is equal to 1. So if I do y equals 1, it's gonna say false, 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 true, 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 true. Okay. So I am just going to add 1 to anything. I'm gonna add 1 to anything where y is true. And the reason why I'm doing this is okay, actually, let me do this first. If I don't do that, all the points are like mixed in together. So essentially all I'm doing is I'm taking the blue points and I'm adding 1 to them to shift them all up so that
Why
There.
didn't you just do that in line 9? Just put -1, 2.
yes. So you could. Yeah, you could do that if you wanted to. Yeah. But the idea is basically is like I make random points and then I'm kind of like separating them a little bit just for the purposes of this exercise. Oh, wait. Didn't I set seed? Why is this different?
Sorry, I messed it up.
Did I? Okay. Well, this is what it's supposed to be. Okay, great. Anyone have any questions about this? Okay. So we're gonna just put this into a data table. X, y equals x dot factor y. And we are going to use our SVM, so we are gonna run a support vector classifier, which is just a, SVM is a generalization of the SVC, right? It is a SVC, the support vector classifier, is an SVM using a linear kernel. So we use a function called SVM, and then we're gonna specify that we wanna use a linear kernel.
So there's gonna be different options in the kernel for the SVM
Yeah,
function.
yes. And we'll look at different kernels in just a second. So kernel equals linear. There's something called cost. And I have I'm totally blanking on what the cost is, so let me. Grab that really quick. Oh yeah, sorry. The cost is RC. This is the number of violations that you are allowed to have. Okay. Or sorry, it would be our epsilon. No, that's right. It is the C. The C is the total budget. The epsilon is the actual number of violations. Okay, so I can run this guy. Summary SVM fit.linear. we have 2 classes, 6 support vectors, right? So it only is going to draw this support vectors for the points that are being considered in the definition of the hyperplane. And let's look at a plot of this. Okay. So it has drawn a line here. So this is our linear hyperplane. And from a predictive standpoint, right, the hyperplane is separating things into where it thinks the value should be -1 versus 1 as I go through my x1 and x2. This is like graphs inversely from the plot, because we have v1 over here and v2, but okay. Right? So it looks something like this. The x's, what do you guys think the x's are?
Violation?
So it's actually not the violations. The x's are the support vectors that define this hyperplane. Okay? The violations are by color. So it doesn't actually tell you, but you can kind of just look and see, right? So if you're red, you're in the red territory. If you're black, you're in the yellow territory. So how many violations are being made here? 2, right? So this one, red, and this one, black. Yeah.
Did you say it's linear?
Yeah, but it's like, yeah, so it's a linear kernel, so it should be linear, but there's some like approximation happening in little bits and pieces here and there. So this would be, yeah, an imperfect representation, but you can think of it as being, it's supposed to just be a straight line. Cool. Okay. Any other questions? Yeah.
If we set the cost at 0, then we'll just throw an error.
Yeah. Let's see what happens. That's a good question. So cost 0, are we actually able to draw? Are we actually able to draw a line through here that would have no violations? Well, let's find out. Error. Can't do it. What about if we did 1? Okay, so what does that look like? So you can do it with just 1. But it may think that
Seems like the support vectors are longer when there's just 1.
yeah, exactly. So, right, the idea is you're allowable up to 10, and so it will continue to violate and examine cases where you can violate points until you find the one with the largest support vector. Largest possible support vector. And so in that case, exactly as what was being said, the SVN, the SVC is actually going to prefer to have 2 violations as opposed to 1 violation, because the support vectors are going to be maximized in that case. Okay? Cool. So, we can take a look at this. So that's our optimal. And let's do a support vector machine radial with a radial kernel example. So I'm gonna load a file esl.mixture.rda. So we'll look at what this looks like. So from this data set, we have this ESL mixture thing, and it's got x, y, x new prop, so all of this stuff. We're gonna get rid of our x and y from before, and we're going to load ESL mixture. Okay, so let's take a look at this data. Okay, so we've got a whole bunch of red points, a whole bunch of black points, a lot more sort of overlap, and maybe we would want something nonlinear here, right? So if I do something like this. Okay, so SVM fit, we're gonna do a radial kernel this time. We're gonna do our y's on everything else, on the x's. Just so you see what this looks like, I'm gonna do that. It's just our x1 and x2. Scale equals false, kernel equals radial, cost so I should note that the cost budget is not literally only 5 points can be violated. It's actually in reference to a scale, so the larger the number is, the more points that you're allowed to violate. It's a little bit, it's actually a little bit ambiguous how to necessarily set this precisely, because it actually depends a little bit on your end value in the context of the problem. So you may have to like play around with the cost parameter a little bit. Okay, and let's actually look at the summary. SVM fit.radial. So we have two classes, 103 support vectors. So in this case, our hyperplane is actually supported by many of the points. And you'll find that this is very commonly the case in non-linear hyperplanes. Okay, so this is what it looks like here. And you can see all of the x's that are kind of around where the the X's are kind of what's defining the shape of our hyperplane. And you will note that there are like X's that actually go pretty far into here. They're not just on the border. And this is because when we think about the kernels, right, it has this whole bandwidth argument that thinks about points not just localized right nearby. And so, you know, you may have X's all the way down here. In the red area, we have points that are red. In the yellow area, you have points that are black. And we can see that there are some violations, right? So, you know, anything that's red here, how many are there? 4, 5, 6, 7, 8, 9, 10. 10 that are violated on one side, and then 1, 2, 3, 4, 5. Maybe like 17 to 20-ish on the other side. But generally speaking, right, this is kind of this nice classifier tool that can give you pretty good predictions of the classification of each of your points. Okay? And if you're talking about, like from a predictive standpoint, how well you can do, right? Think about the classification of the classification tool that we've talked about before with like a logistic model, right? This is a lot more flexible, and so predictively, it will often at least do as good as a logistic model, if not better. Okay, so this you can think of kind of as more analogous to our k nearest neighbors example, but it's doing this with kernels as opposed to that k nearest neighbor algorithm. So from a predictive standpoint, generally these models are going to do a lot better than a logistic model, which is going to be constrained to have linear hyperplanes. Okay, but remember that with a logistic model, I can say something about how the probability that an outcome is one particular outcome as the variable changes. Here, you're gonna have a much harder time saying that, right? Because imagine if the logistic function was just this defining line, then it says as you go from x2 from here to here, the probability, right, of me being, you know, on one side versus the other is some amount, and that changes. You can't really say that here, right? This is only going to tell you predictions for one side or the other, right? So same story that we've been talking about in terms of interpretation and reasons why you might choose one over the other. Logistic model, right, keeps some of the interpretability, much in the same way that a linear model keeps some of the interpretability with the betas, compared to like an SVM analogous to like a kernel regression, right? With the kernel regression, we can't say anything about how our inputs are necessarily changing our outputs, but we can make predictions based off of whatever inputs that you're telling me on what the output would be. Okay? So this harkens back to the thing that I was showing you at the beginning of class, right? This is kind of solidly a tool for prediction. And this is kind of our first foray into, I guess, what a lot of people would call machine learning techniques for classification. Okay, any questions? Yeah.
I probably said this at the beginning, but can you talk about the cost equals 5? Aren't you in violation of that?
Yes.
Can you repeat the question?
I was saying, isn't he in violation of the budget of errors? Like,
Yeah.
Okay.
Right. So the thing that So I was explaining, so this cost is not strictly telling you the budget, it's kind of like a scale of your budget, and so it's not saying you only have 5 violations, it's more, you can think of the cost more as the larger the cost, the more violations I'm allowed to have.
Okay.
It's like a tuning parameter.
Right.
So it's kind of tricky to like nail down what the tuning parameter needs to be. You want it, you basically just want it large enough that you get enough flexibility to get your SVM to the right spot. And that's the part that I was saying that you can try and figure out using cross-validation.
Mhm.
Yeah. Because the more violations you're allowed to have, it's kind of like the thing that I'll say, like it's like more squiggly, right? Yeah.
Yeah, on that, the prior was 10, but the violations were 2. So does it automatically try to minimize?
It'll try and maximize your support vector thing. So, yeah, you want some balance in your cost value so that it's able to do its job correctly, right? You want it large enough that it settles into a particular hyperplane, but you don't want it, generally you don't want it to be too large. You run into this computational issues with doing all the kernels. Did you have a question?
We're trying to minimize the number of violations here, right? I mean, how do we?
No. So you set a tuning parameter that will tell it, okay, you have some budget for violations, but the thing that it's actually optimizing is not trying to reduce the number of violations, it's trying to make it so that the support vectors are as large as possible. That's the thing that it cares the most about. And so if I can make a hyperplane that has a really large support vector, and I only need to do like 2 violations, even if I have a budget of like 3 or 4 or 5, if that's the one that gives me the largest, it's not going to do more violations. Yeah. Yes?
How does it choose, or do we tell it to choose X's over O's?
No. X's and O's. X's are,
That's supporting vectors.
yeah. X's are the ones that are actually helping define the hyperplane. We don't choose that. Like the algorithm figures out how to do that.
It's never going to choose the O's. But there's a bunch of dots that are O's that could in theory also form a vector of supporting.
Yes. So if the shape changes, you could have circles being X's, but let's assume that the algorithm does its job correctly and this is your best hyperplane, nonlinear hyperplane. You could get rid of all the O's in this plot and nothing would change. But if you got rid of an X, then the hyperplane would change. Okay?
Like, that's a huge deal. If there
Yeah.
would be no circles and it would have the same shape,
Yes.
then they're irrelevant.
Yes.
So it's like they're noise.
No. So,
Those are the points, right?
yes, all of these are like the points in your data. I don't know ahead of time which points will determine what the support vector will be, right? Until you run the algorithm, it's not going to know that. And once it's done finding the right one, this is telling us is that, hey, these are the points that are the ones that help me build this hyperplane.
So it could be the circles. Maybe.
Sorry, what?
If all those are data points,
Yes.
but they're differentiated somehow into circles and X's, the algorithm could choose to base its work on circles.
The data isn't differentiated as circles and
Yeah.
boxes.
The data is differentiated by black and red. Okay. So there's no circles or X's in the data. So as this hyperplane is drawn, right, So, okay, the way that you can think about this is, okay, we have all of our data, don't pretend that there's no circles and there's no X's. Okay, but do pretend that they're red and black. Okay, so we have all of our data, and we just start drawing some hyperplanes. Okay, here's one hyperplane, here's another hyperplane, here's a third hyperplane, and then if we do nonlinear kernels, here's one hyperplane, here's another hyperplane, here's another hyperplane. Okay, the hyperplanes are defined by some group of points here. Okay, you draw support vectors to like build that hyperplane. This hyperplane versus this hyperplane versus this hyperplane, one of those hyperplanes will maximize the support vectors. Okay, and it just so happens that this hyperplane that was drawn, of all the hyperplanes that we looked at, is the hyperplane that maximizes the support vectors. Okay, so I figured all of that out, and now I can say, well, this hyperplane is defined by some of the points in here, right, the support vectors, and those support vectors are the x's.
You could have chosen black over red at the beginning.
Yeah, yeah. Okay. Any other questions? Yeah, so explore this tool. It's a pretty handy way to do predictions. Again, if you don't necessarily care about inference, this tool is going to be at least as good as a logistic regression at predicting outcomes, if not like way better. So that is SVMs. And that's it for today. We'll, like I said, probably end a little bit early. I'll stick around if folks want to talk about anything. I know that some people want to talk about projects, and so happy to spend some time to do that with you guys individually. Okay? Otherwise, I will see you guys on Wednesday.